Okay, so all good things in this world come to an end, including my lectures. So this will be the third and the last one, and we will be talking first about quantum mechanics as like mechanics, real mechanics in the quantum regime. And then, time permitting, I will tell you about our work on application of quantum sensing in biomedical research. So, this you have seen before. Okay. Oops. Well, you can learn it by heart. Could it be something with the computer?
We cannot not tell disease.
Let's just get a presentation.
Sorry.
Thank you. All right. So, you have seen this before, and this is the known equation for the oscillator energy, and we can calculate the zero-point fluctuation size. So the energy corresponding to the zero-point motion, that is to say, the oscillator is at zero temperature. And if you have done quantum optics, you actually learned that zero-point fluctuations of the electromagnetic field, they exist. But this is something kind of weird, right? Because we know that if you sum over all the modes of the electromagnetic vacuum, then those zero-point fluctuations will diverge. With mechanical oscillators, it's different. You can cool down the mechanical oscillator to the absolute zero, and you can observe the zero-point fluctuations, and I'll show you how this works. So one can calculate what's the size of the zero-point fluctuations, because you can just take the energy of a normal oscillator and equalize it to the 1/2 of the h bar omega, which is zero-point energy. And if you do this simple arithmetics, then for oscillators that we have, which I will show you in a minute, you'll get about 1 femtometer, the size of those zero-point fluctuations. So that's our oscillator. It's a quite visible piece of dielectric of the size of fraction of a millimeter, very thin, but you can certainly see. And it oscillates at a megahertz frequency. 1 femtometer, is it small? Well, it is small. But if you put this thing in a cavity, measuring 1 femtometer displacement is a piece of cake. You do it all the time. It's not a problem at all. You just need an oscillator, I mean the optical resonator with a finesse of maybe 1,000 or 10,000. You can do it. There are other problems. So for this oscillator, the frequency of oscillation of this drum mode is in megahertz. The weight is 10 nanograms. So this is arguably one of the largest and heaviest systems in the entire wide world, which you can bring deep into the quantum regime. Okay, so phonon state. This thing oscillates, and you have 0 phonons, 1 phonon, 2 phonon, whatnot. The Hamiltonian of free motion is kinetic energy plus potential energy of an oscillator, and you can rewrite it with the h bar and the frequency of oscillation and p squared plus x squared, where p and x are the dimensionless quantum variables for an oscillator. And this is how you define them. You define x as normal x normalized to the 0-point motion, and p like that, And this is the size of the 0-point fluctuations, and this is how you can get the 1 femtometer that I just calculated. So the mass of 10 nanograms, the frequency of a megahertz, the H bar of H bar, and you get 10 to minus 15. Like that. Now, the issue with the thermal noise of the mechanical oscillator is that mechanical oscillator couples to temperature. If you remember, maybe you don't remember, but I made some big deal of the fact that the oscillators made of atomic spins, remember? Many atomic spins oscillating, and I proudly told you that we can actually initialize it in the ground state of the spin motion. And I give you reasons for that. With this guy, it's very different. You have to fight, because at room temperature, this oscillator will have about 1 million phonons in it. And how do you find this million? Well, you take KBT, which is the energy, and you divide it by h bar omega, and lo and behold, you get 10 to the 6, 10 to the 7 for the oscillator with 1 megahertz frequency. There are other oscillators in this quantum mechanics. There are oscillators with the gigahertz frequency, and those you can actually put in the ground state by putting them in the dilution refrigerator. We don't want to do it. We want bigger, nicer oscillators. So we have to cool them by using light. So we use light to cool the mechanical oscillator. Yes, so this is what I just told you, that at 4 Kelvin, for example, the oscillation amplitude is about 10 to minus 12 meters, and this corresponds to about 1,000 excitations in the amplitude or 1 million phonons. So how do you study such things? Well, easy. You make a resonator, standing wave in the resonator, light comes in, makes a standing wave, and you put your oscillator right here, and it oscillates. So when you put a piece of dielectric in a standing electromagnetic wave, what happens is that if, for instance, you put it in the maximum, then actually nothing happens. Because near maximum, the derivative is 0, and so you can move this piece of dielectric and have no effect. But if you put it somewhere on the slope, then when this oscillator moves, it couples to a weaker field, to a stronger field, to a weaker field, to a stronger field, and it modulates this field. And so, if this is the transmission spectrum, the resonance of this cavity, optical cavity is a resonance, and if, for example, you're driving with a laser at blue detuning, as we say, from the resonance of this cavity, that is to say, you detune your laser so that the frequency of the laser is higher than the resonant frequency of this cavity. It still couples in, and then, because you have a piece of dielectric which is moving, it's like a modulator. It creates sidebands of this laser at the plus and minus frequency of the oscillation. It's like an acoustic modulator in some sense. So, if we look at it from the quantum mechanical perspective, then what happens is that if we have the laser detuned in this direction, then this sideband is in resonance with the cavity and it's very happy, and this one is out of resonance and it's not happy. So what happens here is that you predominantly create those sidebands. So if you come up with a laser, which is shot noise limited. It has no light in those sidebands. This light will appear because the modulation will create the sidebands, so the photons will scatter from the laser into the red sideband in this case. In terms of the Hamiltonian, this process will be defined as creation of a photon in the red sideband and creation of a phonon. So this is an entangling Hamiltonian. We discussed it before in the lectures. So if you have this kind of detuning, then you will create entanglement between phonons and photons. On the other hand, if I just tune my laser on the other side of the resonance, then the blue sideband will be efficiently generated. So photons from here will be scattered in this mode. This mode has a higher frequency than the laser. This energy should come from somewhere, and it comes from the phonons. So you have the creation of the blue sideband and the annihilation of the phonon. This is actually cooling, because I'm taking the phonons from this oscillator and putting the energy into the light mode. And this laser has an infinite thermal capacity, so to say. So it can cool this thing easily. Well, easily. The cost of a couple of PhDs. If on the other hand, you put this laser smack in the middle, then both processes happen. So you have to add those two with equal weights. And if you heard my lectures attentively, then you would say, aha, if I have the sum of those terms, then I get a QED interaction, quantum non-demolition interaction. Because it's like A dagger B dagger plus A dagger B plus Hermitian conjugates. You can rewrite it and you will get the x of mechanics times x of light. Wonderful. So by simply moving the laser resonance with respect to the system, you can implement any kind of bilinear Hamiltonian that we talked about. Right, so if you put it smack in the middle, then as we said, we will have the quantum non-demolition Hamiltonian, and we actually know what's happening if we apply quantum non-demolition Hamiltonian to the system. We talked about it in the language of the spins, and it's the same here. So you shine light in, and light coming out, or reflected for that matter, will contain the shot noise of coming light, plus the information about the position of the mechanical oscillator with some coupling constant. What is this coupling constant? Well, here it is. So kappa, in this case, is the bandwidth of this optical resonator, and G is given by that. So it's optical frequency, the length of the resonator, the mass of the oscillator, the frequency of the oscillator, h bar, and the number of photons in light. Well, photons are G. I can get any number of photons. So this is another wonder of the world. In this interaction, at least for a theorist, there is no limit on the coupling strength between quantum mode of light and quantum mode of this mechanics. So feel free to get whatever number you wish. For us poor experimentalists, life is not a beach, so there will be a lot Okay, so using those very nicely designed mechanical oscillators, and the reason why it has all those holes is because you want to isolate the motion of this drum from the environment as good as it gets. So this is the so-called phononic band-gap structure, which actually only allows certain frequencies to couple from the environment into this thing. So what you see here is the spectrum of oscillation of this whole thing, and this is within the band gap. So you see nice and pretty oscillation of this membrane, and outside there's just horrible, don't go there. Now, in terms of the readout, we discussed it already for the spins, and it's a very similar story for the mechanical motion. So you send light in, and you get light out, and it's the short noise of light plus whatever force terms lead to the motion of this membrane, for example, thermal motion, plus the back action. And again, the short noise of light is one quadrature of light, and the back action is the orthogonal quadrature of light. So no news here. You see, like, why a person like me and people who work with us got very happy about those optomechanics, because we've been working with spins and we love them. And then when optomechanics grew, up to age, and people learned to make reasonably good mechanical oscillators, for us it was very natural to go into this role. Yes, so this looks very similar to the spins, but it's now for mechanics. So this frequency is the frequency of the mechanical oscillator. I cannot tune it as easily as I tune the frequency of the magnetic oscillator with magnetic field, but that's what it is. Depends on, the mass of the tensile stress and all that, and we can fabricate those things in a good way. And again, what you see here is something which is completely dominated by the quantum back action, because the ground state noise is super negligible here. So by cranking up the intensity of light, as I said, we can get very high comparativity, meaning that we are dominated by the back action. And if you remember my previous lectures, being dominated by the quantum back action is the prerequisite for generating quantum entangled states. Yes, and this is one of the highlights of this business. So we send light through our atomic spin oscillator, and it goes through the mechanical oscillator and is detected. So this is the spin oscillator that I told you about many times. This is the mechanical oscillator, and this is what light carries on. Again, the short noise of light, the noise from the spin, the noise from the mechanics, and the two back action terms. Again, if we have negligible losses between the two systems, then this operator acting on the spin and this operator acting on the mechanics, they are the same operators, they have the same fluctuations, and they can be cancelled if the multiplication factors here and here are equal and opposite. And since I told you that the spin oscillator can be effectively in the negative mass regime, we do it that way, and lo and behold, this can be cancelled. So a little story about matching those cooperativities or matching the strength of the interaction, because this is what we require to have the back action cancelled. I told you that the optical depth is essentially the key parameter of the cooperativity for the atomic space. And we just want to make it as large as possible. The mechanical cooperativity, or this G coupling constant, I told you already about it, so we just essentially need to regulate the number of photons in the driving field and tune it in such a way that those two are equal. And here is the wonderful result. So this is on the log scale the spectrum of the mechanical oscillator centered at the mechanical frequency. So it's the thermal noise of the mechanics, which is very close to the ground state. I didn't tell you much, but we do optomechanical cooling. So we first cool this thing almost to the ground state, and then we start this process. So there is nice mechanical state, and the rest of it is quantum back action. And again, this is a log scale, so it's really dominated by the quantum back action. On the atomic side, this is atoms tuned away from the mechanical resonance, so that the two systems are completely independent. We can measure them independently. They don't talk to each other. They talk to different modes of light. And again, this is the atomic thermal state, so it's not as close to the ground state as we wish, but it's good enough because it's still on the log scale several times smaller than the quantum back action. And the point essentially is that the area of the quantum back action here and here should be the same, and then they cancel out. And now we put the atoms in frequency on top of the mechanics, and we got this. So again, it's a log scale, so instead of naively imagining that the total noise due to back action will be just the sum of this and that, on the contrary, we get something which is really, really smaller than the sum of those two. It's actually smaller by a factor of 4, 6 dB. So it's a serious cancellation of the quantum back action, and we celebrate it and publish and drink champagne. The next step along those lines will be actually to see, can we generate entanglement between those two distant and very different oscillators, the mechanical oscillator and the magnetic oscillator. Because suppressing the back action is the necessary but not sufficient condition for generating entanglement, because if the oscillators, if their own state is rather far from the ground state, then you can suppress the back action, but you will still have a lot of extra noise. And yeah, I would like to stress that Rodrigo Thomas, who was the first author in this paper, is actually a proud Brazilian. So he did his master's at this university and then came for a PhD to my group and then stayed with me as a postdoc, and now he is a researcher at another group at the Niels Bohr Institute. And another Brazilian that works with us quite successfully is Túlio Brazil. Maybe some of you know him. He's from São Paulo. Okay, so let's look at this entanglement generation. So I understand the audience is dominated by theorists. How about Wiener filtering? Does it ring a bell? No. Okay. In fact, I strongly advise you to look for it in the literature. So Wiener filtering is essentially filtering of a signal which is optimal for measuring a quantum state. Like, you have a signal coming from a certain quantum system and you want to estimate its quantum state. So how do you do it? If you just keep measuring, it's no fun, so you need to do tricks. But, so this is the layout of the experiment. Light goes through the atomic oscillator, comes through, another local oscillator comes in. Why? Because with atoms, if you remember, the local oscillator and the quantum fluctuations were in two orthogonal modes. Whereas for mechanics is not sensitive to the polarization. So for mechanics, quantum fluctuations and the driving field, they're in the same polarization. So we need to strip off this local oscillator here, and that's this polarizing beam splitter is doing. And then we add another local oscillator and interact with the mechanics, come back and do the homodyne measurement of the field that comes through. So we take this photocard and we separate the sine omega t and cosine omega t. We can do it radio electronically. And again, if you remember my story about atomic systems, then you may remember that in the rotating frame for the spins, sine omega t would give you the information about one quadrature, and cosine of another quadrature, same here. So when the oscillator oscillates, there will be a sine and cosine components of this oscillation, and you can look at them separately by looking at the cosine and sine component of this photocard. And of course, both of those signals are very random, because we're shining light on this system, and this light is shaking the whole thing. But if we apply a suitable filtering, and this should be the rising exponent, and then we measure here, and another rising exponent, and we measure here, and we apply it to both cosine and sine. And if we do it right, then we actually estimate the quantum state of the composite system at this point in time, and then at this point in time, and then at this point in time. So the duration of this measurement process should be much shorter than the decoherence time, obviously. So you need to play well with it. But if you do it right, then you have this conditional dynamics, conditional on this measurement. So you can make an estimate of the state, and then using the falling exponent, you can verify that what you're measuring with the falling exponent is entangled with what you're measuring with the rising exponent. And this will tell you, oh, I generate a state which I actually can predict. And this is essentially entangled by measurement in a little more involved scenario. So, if we're lucky, I can show you this story. So there is a video here, and this. Here we go. So, admire this. What you are seeing is the prediction and retrodiction of this signal. And the key point here is that the prediction and retroduction are close to each other. So the blue circle is the standard quantum limit. And as you can see, the prediction and retroduction are well, so the difference is well within this quantum limit. So we can actually predict it and then measure, which means that we know the sum of excess and the difference of p's with the precision which is better than the standard quantum limit. So again, remember we talked about it, that if you have two entangled systems, then each of them is actually in a completely random thermal state. But the point is that when they're put together, then they are very entangled and very correlated. Anyways, so this is another demonstration of the same story. So for magnetic oscillator, remember we talked about it, its state is relatively close to the ground state, whereas for the mechanical oscillator, because we cool it, but we cool it of course, but still if you wait long enough, then a stray photon will jump from the environment into the oscillator and change its state. So we only have with the mechanical oscillator, we have limited time to play with it. During this time, the state of this oscillator is well defined. So this is what I'm trying to show here, that inside this thermal state, the state of the oscillator changes rapidly, but we have 300 microseconds during which it, roughly speaking, doesn't change. And so now we make a measurement. This is the back action on one oscillator, this is back action on the other oscillator. But if they're entangled, that means that they're well correlated for each given moment in time. We don't know where they are, but we know that they're correlated, and this is what we have proven in experiment. Right. So, how much time do I have left speaking?
You have
40 minutes. Oh. Okay. So, I'll tell you now about the quantum sensing in health applications. As I mentioned at the start of the lectures, we started a new Center for Biomedical Quantum Sensing, and it's a year old and we have many years to go. So this is like a propaganda scenario, propaganda slide for quantum sensing. So quantum technologies, there is computing. Is there computing? No, there is no computing. We're on the way to the computing for the past 25 years, making big progress. We're on the way to the computing, and everybody believes that the first useful computing will be actually quantum simulations, as Feynman predicted ages ago. It's a wonderful story. Lots of people working on it. God bless them. The quantum communication is a lower hanging fruit. So, people have demonstrated quantum cryptography. The first experiments 25 years ago. It's getting better and better and better. The quantum repeater is still yet to be demonstrated. Who knows what quantum repeater is? Oh, please, go to the Web of Science or whatever. Go to Google and Google what this is. Quantum repeater. It's super important. Anyways, so this requires 1 qubit per pulse. This requires 100 maybe 1,000 qubits. But with quantum sensors, the more qubits, the merrier. I just told you about the system which has, 10 to the 10, 10 to 11, 10 to the 12 individual qubits, and we happily use them for sensing. The difference, of course, is also in the states that we can generate, because here they are thinking of the maximally entangled states. We are not in the maximally entangled business of 10 to the 12 atoms, but we're good enough if we have quartets or quintets of those atoms entangled, and that brings us to the spin squeezing and entanglement. So, one of the main kind of general directions of quantum sensing is, of course, sensing of electromagnetic fields, because what else do we want to sense? Well, we can sense the gravitational wave, and in fact, in my talk at the conference on Monday, we'll be talking about our efforts in this direction. But by and large, all applications are about measuring electromagnetic fields. And as I already told you, STEM quantum limit is the balance between precision and back action, and then sensing beyond this limit is enabled by entanglement. And you have already seen this story, so this is one of our first experiments ages ago, where we demonstrated entanglement between two oppositely oriented spins. So you've seen this before. But the point is that if we can generate such an entanglement, then we can then apply the field of interest, magnetic field, for example, to one of them without touching the other one. And so this one will change its state, and you can detect this change by looking at this thing again. So before the external perturbation, you make those two spins exactly antiparallel by entanglement, and then you subject one of them to the external perturbation, and then you can measure. And you can measure both projections of the spin on this axis or on this axis. So you can measure the entire trajectory of the spin. And we have done that, and we achieved, sub-femtotesla sensitivity. I mentioned already that in the morning. So we've done experiments with a hamster heart, for example, and yes, we can measure the hamster heartbeat. We haven't used entanglement in this particular measurement yet, but we will certainly do that. So the work is relatively straightforward again. You take your paper cell, you optically pump it, you probe it, and the magnetic field generated by the heart affects the spin, and it moves according to the heartbeat. It's a tricky business because the heartbeat is rather slow. So, this peak, well, the separation from this peak to this peak for a human heart is a second. For the hamster, it's a little shorter, maybe about 300 milliseconds. But the width of this is more like in the 10 millisecond range, so you still need high frequency resolution, and we achieve that. And we collaborate with the local hospital in Copenhagen, and they seem to be happy about it. So if one day we can take the spin squeeze state of atoms and apply it for this measurement, and we hope to do it soon, then we can improve the signal to noise here. Life is good. So that would be the implementation of a spin-squeeze state, entanglement of atoms, for some real medical diagnostics. So, once again, if we want to use entanglement of this huge number of atoms for something real, then only very special states will survive. And such states, which should be highly symmetric, can be single-mode squeeze states, can be two-mode squeeze state, if you are entangled. And they also can be symmetric collective single excitations. I didn't talk much about that, but you can generate a single excitation inside the 10 atoms distributed between them, and that will be like a Fock state of a spin, which is distributed among the microscopic number of atoms. So, suppressing quantum noise and sensing, you have heard about that by now. So, we make a measurement, we are limited by the shed noise of the probe light and by the back action of the light on the spins and by the sensor noise itself. If we use a squeezed light probe, we can suppress that one. If we use quantum engineering, which allows us to suppress the back action, we can get rid of this one, and this I will show you in a second. A side note, I think some of you work with squeezed light, so let me present you the simplest in the world source of 12 dB squeezed light. So what you need is a well-engineered atomic cell, a little bit of good theory, and a nice measurement, and that's it. So, back to the basics. If we have atoms in the magnetic field, then we know that the state will be oscillating like that, right? So the more you measure, the more back action you have. And what I told you about so far is that if we want to get rid of this back action, then we should have two sensors and the back action will cancel out. There is one other way to use this back action, and here it is. So, the light coming out from this machine has the shed noise of light and the back action and the signal. And as it's written now, this quadrature and this quadrature are orthogonal. Can we actually make them not orthogonal? Can we actually make interference between the noise of light and the back action? Remember, one of them is the sine omega t with motion, and the other one is the cosine. So how about we introduce some phase shift and make them interfere? And so for that, we need to make a measurement not of the p of light, but some other quadrature. So a combination of the x and p. And this can be done by introducing a wave plate. So you take a wave plate, and now you have the phase shift between, let's say, linear polarization and circular polarization. So now you're measuring some elliptical polarization. And this is what happens. So, shed noise of light, back action of light, I'm sorry, this thing is a little shifted. So, if you now introduce this phase shift, then you will see that, in fact, there will be a cross-correlation between the back action and the shed noise. And this cross-correlation can have a negative sign because the sign can be negative as well. And so, this is what you get. If you are looking at the noise of light detected by this common detector at the frequency of the atomic spin precession, depending on the phase that you observe here, that is to say, depending on the setting of this quarter wave plate, you have the following dynamics. If there is no quarter wave plate, then you have all your back action, as you expect. If you introduce this interference, then we begin to see something very interesting, and lo and behold, you have this curve, which is actually like 9 dB of squeezed light on the detector, with no losses, corrected. If you correct it for the detection inefficiency, that's 12 dB. Moreover, this you get if you measure for a little while, right? So the measurement time is, roughly speaking, the width, the inverse of the width of those curves. If you measure much faster than the oscillation frequency, you actually can get the broadband squeezing with like 6-7 dB of squeezing stretching from a megahertz frequency all the way down to a few kilohertz. So that's the cheapest, simplest source of squeezed light that I can offer you. We actually plan to put it in a suitcase and put it on sale. Yeah, so like I said, interference between the back action and the shed noise give you the reduction of noise. Okay, so there are many perspectives playing with those room temperature. We can magnetic oscillators, you can use one of them for squeezer, another one for sensor, and so on and so forth. So maybe we can go further. So here is the new modality. I told you a lot about magnetic sensing, so you just measure magnetic fields, which come from the heart, from the brain, and whatnot. But we can do something else, which is very useful in biomedical applications. We can measure conductivity. And a simple example is that your blood, which flows through the heart, is quickly conducting liquid. And if, not in your age, but in the age to which you will one day come, something happens to your heart, God forbid, then the flow of this blood can change the path. And at the moment, if they want to see what's happening, they have to insert some electrodes through some holes in your body. So if we could find out the way to efficiently measure conductivity of the brain or of the heart without actually poking holes in the body, that would be pretty cool. So how do we measure conductivity? Well, that's one way to measure conductivity. It's called magnetic induction tomography. And it's a relatively well-known procedure, except for we combine it with the atomic sensor, which can be in a quantum state. So what's happening here is you have two anti-Helmholtz coils. So the magnetic field, it's AC magnetic field, and it's zero in the middle. So you put AC currents in the opposite directions, you get zero in the middle. And here in the middle, you put your atomic sensor. And now, this coil is closer to the object than that one, and therefore the AC field in the heart will be non-zero. AC field will induce currents. And induced currents, if you remember your electrodynamics, they actually alter phase with regards to the generating current. Therefore, this secondary field will actually interfere with this field, and eventually the field on the sensor will be non-zero. So you can detect this non-zero field by looking at your spins. You can measure the spin direction pretty well. And so the point here is that this oscillation will actually happen at the AC field frequency. And this AC field frequency, you can make it 10 megahertz and be completely free of all classical noise. So this is one of those cases which I'm super happy about, where something which promises to be rather useful can actually benefit from the quantum tricks, because it works best at high frequencies where we can suppress the classical noise. Right. So, how do we do that? How do we use this spin squeeze states to enhance the signal? It started with this paper where we demonstrated that we can actually do the so-called stroboscopic quantum non-demolition measurement, and by that squeeze the spin state. And the way you do it is the following. As we have seen many times already, the spin in the magnetic field is oscillating. And as we already heard, if I just send light through, I will just get a pile of quantum back action. What if I don't shine light all the time? What if I only shine light twice the period? So continuous measurement gives a lot of back action. Stroboscopic measurement, twice the period, is back action free. So now you measure, don't measure, measure, don't measure. And so all your back action goes in one quadrature of light. And you can measure the signal with a precision which is better than standard quantum. And this is what we have demonstrated those few years ago. So you prepare the atomic state, you apply the perturbation, and then you make a measurement with stroboscopic fashion, and then you read out the state also with stroboscopic fashion, and then you show that the state is conditionally squeezed. And this is the squeezing result. So you measure, you measure, you measure, and the more you measure, the more you squeeze, and in this case, it's the spin squeezing of about 2.5 dB. Another picture showing how it works. So now we're looking at the spin from the top. The spin is precessing like that, and you make measurements here and here and here and here. And again, in the Bloch sphere, that basically means that the spin is oscillating like that, and you're making measurements here and here, and seeing the spin squeezing. So the result is that we can measure the presence of a weakly conducting sample. We're not yet on the hard measurements, we're going there, but we can detect the presence of a weakly conducting object, and the detection is facilitated by the entanglement between the atoms. So this is the result. What you see here is we're trying to localize the position of this sample. So the blue points and the blue curve is how well we can do it without entanglement, and the red points and the red curve is how we can do it with entanglement. And we get a factor of 2 improvement in the spatial resolution. Well, it's the first result. And in the future, we can maybe use squeezed light to this. Yes, so this method we hope to implement for various types of measurements. This is just the way it is done at the moment, so everything is in the magnetic shield, and there is a probe here, and then you put in a sample, weakly conducting sample, and you make a measurement. Right? So, where we want to be is we want to detect the difference between various kinds of biological tissue, and here we plot the conductivity of different types of tissue like gray matter, white matter, muscle, nerves, heart. And this is our current sensitivity. So if we use some few megahertz magnetic sensing, then we can relatively easily detect the difference between various kinds of biological matter. And we hope to go towards brain conductivity measurements, and we'll see what happens. So, in fact, I'll let you go at this point, or at least let you ask questions. It's pretty dark outside, so maybe we should stop. Thank you.
Thank you very much. This is truly amazing. Questions? Oh, yeah.
One question about your membranes. Could you think also of a way of detecting microgravity, gravitational effects, if that like a Cavendish experiment where you have like this pendulum which gets always smaller and you still detect this gravitational effect?
Thank you for the question. We actually are thinking of using this approach in the real large-scale gravitational wave detectors. So on Monday at the research conference, I will tell you how we published a paper just 3 weeks ago where we demonstrate the way to use those atomic noise eaters to suppress the noise in the gravitational wave detector. So what you are talking about is probably interesting. I'm sure it is interesting, but we kind of concentrated on the existing technology. I'm happy to talk about your question later on. Thank you.
Thanks.
More questions?
In the back.
Hey, thank you, Eugene. For this last part of your talk, particularly, for instance, about measuring brain conductivity, how do these systems, these atom-based systems, perform when compared to existing contenders like squids, for instance? in terms both of sensitivity, but also, like you mentioned, frequency of operation?
Well, they perform infinitely better in terms of the price. So, and also in terms of compactness, we hope to achieve similar sensitivity. The limitations in squids are the distance and the bulk nature of this whole golden thing at liquid helium temperature. So this is our competitive edge. Their competitive edge is the multi-billion-dollar industry, which is there. We'll see who wins. Well, I think, seriously speaking, there will be, hopefully, the niche applications for us. Like, if you have a small baby, maybe it will be easier to put on her head a little set of room temperature sensors rather than put the child inside the squid operation. Whatever. We'll see what happens.
More questions?
Thanks again for the talk. So, which I understand is that for each sensor that you have a measurement of you have the intensity of the field. But do you have information about the direction of the field also?
It's a good question. So the direction that we're sensitive to is defined by the induced currents, right? So if you have the field is basically, axially symmetric. So the currents it induces will be sort of radial with respect to this thing. So one day we will have several of those sensors and we will need to do the tomography, and there's problems in all this business. So we're on the way in this direction. Thank you.
So, do we have any more questions? No? If not, let's thank Professor Polzik again.